All right, so this video is going to be on halogenation of alkyl benzenes, as well as some oxidation reduction of some benzene compounds, and then I'm going to throw in a nice little reaction that's going to complement your electrophilic aromatic substitution reactions. Okay, so this is our general trend. We already knew increasing radical stability as we get to the allylic group, but remember benzylic radicals are actually more stable. And that's obviously because we have tons of resonance, right? And so this is kind of the point of the conversation, or lecture in this case, that we can utilize the stability of these benzyl radicals and do bromination. Okay, so it's very selective, and you will get the bromine at that benzylic position, even if you had like a long alkyl chain. Again, remember bromine is very selective and will essentially remove the hydrogen atom that is the weakest and forms the most stable radical. Okay, so here's our benzylic bromide, right? Now, what's the use of this, right? Well, we're getting to the point where we have tons of reactions in our toolbox, and so we can use them to create new compounds. So we just throw in a hydroxide, we can get that alcohol, hit that with PCC, and now we've got benzaldehyde. And you know I like benzaldehyde, right? Stick around to the end and I'll give you a little treat at the end. So let's check it out. Here we got ethyl benzene, for example. We hit it with bromine and some light. You get the substitution at the benzylic position, of course. Hit that with hydroxide, or maybe more specifically like a tert-butoxide. That way you get elimination. I don't know what I'm drawing right now. Let me hit that beta hydrogen to get that elimination product. And then here we have this cool compound called styrene. And you know, radical polymerization with styrene yields polystyrene, which is styrofoam. Okay, so that's what you can do, right? Like, you got plenty of options here. So here's the thing about bromine with some FeBr3. What do you think is going to happen now? Well, we got the cyclohexyl group on there. We're going to hit it with the ortho position or the para position. So here's the thing. You need to make sure that you're aware of what you're doing. So if you have radical conditions, you do radical reactions. If you have electrophilic aromatic substitution conditions with that Lewis acid, then you do that reaction. Okay, so we've got tons of reactions with bromine now, and we need to be careful what we're doing. Okay, so here's the mechanism. Not that we need it because we already know how to do this, but it's nice to see things over and over again. That way they're just stuck in your head, right? So that propagation step, we're grabbing that benzylic hydrogen atom, yielding the benzylic radical as well as HBr. Okay, now we can take that benzylic radical and then have that react with an additional equivalent of Br2 that yields the desired benzylic bromide compound as well as another Br radical. Now this Br radical can come back around and react with another toluene or methylbenzene and get it going again. So that's your propagation step. So termination, of course, is when you have two radicals coming together and the reaction would be quenched because it's eliminating the presence of that radical. So two Br radicals can come together forming elemental bromine again, or technically you can have two of these guys coming together, these benzylic radicals, and you would get this guy. Sorry, actually, pay attention. There's two methyls on each of those benzene rings. So, all right, there's two methyls total, and so we got to make sure we have all of our carbons present when we are drawing the final compound. Common mistake. Me too. All right, so moving on. So we're just cruising through some reactions in this particular video because it's kind of stuff that's complementary but not really worthy of its own video. So we've got oxidation and reduction of benzenes, substituted benzenes, right? And so let's take a look at the oxidation steps first. Okay, so if we hit toluene or methylbenzene with potassium permanganate, we're going to get a carboxylic acid. And so obviously the oxygens come from the potassium permanganate. Okay, and let's see, we've got isopropylbenzene. We'll hit that with there too. With the potassium permanganate, we get the same exact carboxylic acid. So this is important because notice we have the blue carbon, it is the carbonyl, right? That's the benzylic carbon. And the red ones that are boxed are gone. So those are no longer around. And you need to make sure that you're aware that these guys leave. Okay, what about this chicken foot benzene, right? Tert-butylbenzene. Actually, this reaction does not proceed, and you do not get anything. You'll just get chicken foot benzene, right? Tert-butylbenzene after that. And the reason why this is the case is, I mean, take a look at the first two starting materials, right? What's the difference between each of those and the tert-butylbenzene? Well, if we take a look, draw out the hydrogens, you can see that obviously the toluene has 3 hydrogens on that carbon, benzylic carbon, and then isopropyl is the one. Benzylic protons don't exist on the tert-butylbenzene. So that's the reason why this reaction doesn't proceed. Oxidation of alkyl benzenes requires the presence of a benzylic proton, and you're always going to yield that benzoic acid, okay? So, reduction of aeroketones. Before we talk about reduction of aeroketones, I want to bring up or remind you of Friedel-Crafts alkylation and some of the limitations associated with that, right? Or one of the limitations. So if we did Friedel-Crafts alkylation with the chloroethane, we easily got that ethylbenzene, right? But remember when we did Friedel-Crafts alkylation with the chloropropane, it underwent a rearrangement and we ended up with isopropylbenzene, right? So this rearrangement, that's a bummer. That's definitely one of the limitations of Friedel-Crafts alkylation because we can't get linear chains greater than ethyl. And so what if we wanted to get this linear propylbenzene? Well, that's where the reduction of aeroketones comes into play. And so let's check it out. What we want to do is there's 2 different types of reactions, okay? So there are 2 different options for this reaction. We've got the Clemmensen reduction, which is using a zinc mercury amalgam with HCl and heat, right? So that's kind of gnarly, right? And then we also have the Wolff-Kishner reduction, which uses hydrazine and sodium hydroxide, right? So hydrazine is NH2, NH2. And then hydroxide with heat. So these are some pretty harsh conditions. Personally, I'd rather work with hydrazine than like a zinc mercury amalgam. Sometimes you gotta do what you gotta do. So let's say we had to do the Clemmensen reduction, and we've got this particular aeroketone. We hit it with zinc and mercury with HCl and heat, and bam! What you're gonna get is that linear propylbenzene. What's up? Hey. What you guys know about Big Mama's house? There's Martin Lawrence again, showing up. I'm the man. Woo, woo, woo. Alright, cool. So here's the same reaction with the Wolff-Kishner conditions. Got that propylbenzene, okay? So same thing, same result, different reagents. So that's what's cool about chemistry. You have a variety of ways to make the same compound, okay? So the question would be, well, how do we get that aeroketone? Well, remember that time when we also knew a Friedel-Crafts acylation, where we hit it with an acid chloride, as well as that Lewis acid AlCl3, and then we got this. That was my brother-in-law petting my dog, so that's weird. The balls are apparently very thin here, so we've got this acid chloride forming that acid base, Lewis acid based adduct, which then pieces out, breaks apart, right? And then you form that acylium ion, of course, which then gets attacked by the benzene, and then after reestablishing aromaticity, then we get that desired compound, right? So here's that carbocation intermediate, of course. that aluminum chloride, boom, 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 and then get that aeroketone. Okay, so there's also HCl and aluminum chloride as our products, or one of our byproducts. So that's all she wrote for the reduction processes. You don't need another mechanism, so that's cool. The Wolff-Kishner one, I might introduce the mechanism later when we get to amines and their reactions with carbonyl groups, but for now, that's what you get. And then let's say we have this target molecule. So we have benzene. Let's say we wanted to do like this particular alkyl chloride, hit it with aluminum chloride as well. Well, what you're gonna get is this Lewis acid base adduct, and then you can get a quick little rearrangement, just like we have like a 1,2 hydride shift. We can do a 1,2 alkyl shift. That 1,2 alkyl shift will yield a tertiary carbocation. That's why it happens. If you can do that with the simple methyl shift, it's very easy. If you do, obviously the hydride is very small as well, so that's pretty easy. And then we get this kind of branched compound added to our benzene ring. That's clearly not the desired compound. And so what we need to do is add an acid chloride with the little chicken foot, right? So I've highlighted in red the benzylic carbon and then the carbonyl carbon. Those are the same carbon. And that's really how you know what kind of carbonyl compound you want to add, right? What kind of acid chloride. And so once you do the Friedel-Crafts acylation, hit it with the reduction, then you get your desired product. And that's it, right? So that's pretty chill. Let's say we wanted to make this particular compound. Well, let's take a look-see. So we want to start with benzene. That's that retrosynthetic arrow, right? So benzene, we have a couple options, right? We've got two substituents on there, so we can go for the carbonyl first, and then we hit it, we do the acylation. And then now what we need to do is, that's a primary alkyl halide, right? If we were going to do Friedel-Crafts alkylation. So if it's a primary alkyl halide, then, and we have the option to do rearrangement, then it's going to occur. So primary alkyl halide we can't use in this case for Friedel-Crafts alkylation. But if we wanted to do like Friedel-Crafts acylation, right? We add that carbon in the carbonyl group, have it with the little isopropyl group on the end. But what's the problem with this? We can't do Friedel-Crafts when we already have the electron withdrawing group on there, right? So it's a deactivated benzene ring, and so we can't hit it with Friedel-Crafts, which means we need to change our order. So we've got to add that X'd out acid chloride first. Okay, so what that's going to do is give us, of course, the ketone product, right? And then we can hit it with some reduction reagents like Wolff-Kishner, the hydrazine and hydroxide with heat. And that's going to give us our reduced alkyl benzene, which is a isobutyl benzene. And then after that, it's an electron donating group, right? So it's also an ortho-para director. And so we can hit that with the Friedel-Crafts now to put our acyl group on the para position, and we have obtained our desired product. Voila. That's the fun part of this type of chemistry now, is that we have to be selective and kind of choose our reagents wisely, and the order as well. So the kind of like the last reaction in this particular chapter is the reduction of nitro groups. And this is pretty straightforward as well. We don't need to know a mechanism. We just need to know the reagents, H2 and palladium on carbon, or iron and HCl, or tin and HCl will reduce that NO2 group to an amine. So remember, the easy way to remember this is that when you have an elemental metal, it's typically just going to reduce things, right? We saw that with zinc and mercury, or and then we see that now with palladium and iron and tin. right? I'm not sure if I said zinc before, but SN is tin, and we get the amine product after that, okay? So that's pretty much it. So now here's that extra stuff, right? That good stuff. I want to teach you how to make this particular compound. It's a 1,3,5 tribromobenzene, okay? Now, bromine, as we know, is a deactivator, but it's also an orthoparadirector. So all these guys are meta to one another. So how the heck did we do that, or how can we do that? Don't worry, I got you. I got all the tricks in the book for you. Remember also that we couldn't really do the F2 reaction for the halogenation of benzene to get fluorobenzene, right? Because that was pretty wild. The iodobenzene also wasn't really going to be working out for us. So here's the trick: we got to hit it with the diazotization, right? Diazotization means we're adding a diazo group to the benzene ring, okay? What the heck's a diazo group, okay? Well, if you don't know, you're going to learn today. And you hit it with NaNO2, so you hit aniline with that, right? Aniline, when reacted with sodium nitrite and HCl, forms an N2 group on that benzene ring. Now, that looks like an NN triple bond with a positive charge on that nitrogen. Okay, so this is a diazo group, and it's actually, if you can imagine, nitrogen gas can very easily leave, and it is a great leaving group because it's a gas, so it's like entropically favored as well. So if it were to take some protons or some electrons with it, it would leave as N2 gas, leaving a positive charge on that benzene ring. Now this is not going to happen because that's a highly unstable intermediate, but it reacts as such, right? So let me show you the mechanism real quick, and then I'll show you what we can do with that diazo group and the reactions to give us some cool stuff. So that nitrite reacts with the HCl to form nitrous acid, so NO2H or HNO2. That's nitrous acid. And of course the aminobenzene is aniline. Just a quick little reminder for you guys. We do have another equivalent of HCl in there, so of course we can protonate that oxygen. Now what does that form, right? It forms the oxonium intermediate, which is of course just water ready to leave, okay? So we got the positive charge on that oxygen. Now what happens when water leaves? Whoa, simmer down. That's how quick it leaves, you know? All right, so water left, right? And we would have, it takes those electrons with it, right? So that nitrogen is now positively charged, right? This is called a nitrosonium ion. Okay, so it's a NO positive, right? Very susceptible to nucleophilic attack by a good nucleophile, right? We got that nitrogen there with the lone pair. Of course, it attacks, and then we've got a nice little intermediate drawn here. So we got that nitrogen bond starting to look a little bit more like that diazo group that we want, right? So now we got a positive charge on that nitrogen. We want to neutralize that, but we also want to get rid of that oxygen and create some more nitrogen bonds, right? So of course we'll swoop on that proton with some base that's present, and of course why not just use water? That's fine. Once we remove that hydrogen, we've neutralized that nitrogen bound to the benzene ring. And what's a great way to make oxygen leave? You might as well just protonate it, right? Protonate it twice. So here's the first step, though. So we've got the nitrogen single bond with the double bond to oxygen, and hydrogen on it makes it a plus. It's an oxonium, right? So the two steps right there, kind of bracketed, that's a proton transfer. We basically removed a proton from the nitrogen and then put it on the oxygen. So what you can do to kind of skip that step or just draw less is go follow that blue arrow. So go from the ammonium and then draw an arrow, proton transfer, put that, and then you go to the oxonium, right? So, but it is important that you understand this is not an intramolecular proton transfer. It's something comes along, grabs it, something else comes along on the other side and protonates it, right? So once you do that, you can create a nitrogen-nitrogen double bond, and then that stabilizes the charge or neutralizes the oxygen, that positive charge on there. Now we're looking a lot like we need to look, right? So what if we remove that proton from the nitrogen, neutralizing it, and then protonate that oxygen via a proton transfer? Sorry, I'm going to move this over. I've been doing kind of like a book where you read in from a book, so I might as well continue with the arrows like that. Proton transfer yields this particular compound with the water just ready to leave, right? Let's force it out of there, create that nitrogen-nitrogen triple bond in the process, giving us our diazo compound and a water byproduct. I'm so sorry. I got kids. You know that, right? So, yeah, they're loud. And you're going to hear that because we're stuck at home. Bored in the house. Bored in the house. Stuck in the house. Stuck in the house. So, anyway, we got the diazo group right there, right? So, remember that chlorine is going to be the counter anion. And that chlorine came from the HCl, okay? Because we also, of course, we got to form that salt. Okay, so this diazo compound, aka a diazonium, can now be functionalized, or we can use that as a nice starting material to create all of these wonderful aromatic compounds, right? These benzene derivatives. So if we take this diazo group, this diazonium, we can hit it with copper X, so CuX, and where X is going to be our chlorine, our bromine, our iodine. Now we've got all these aryl halides, right? So that's one of the ways you can make the iodobenzene, right? So before the reaction was sluggish and typical electrophilic aromatic substitution reaction. We can add copper cyanide to make that cyanobenzene, of course. Hit it with water and you get your phenol. We know how to do stuff with that now. Sodium iodide we can also make, and potassium iodide we can also make that iodobenzene. HBF4 gets us our fluorobenzene. Nice. And this HBF4 is fluoroboric acid. Okay, so it might be tetrafluoroboric acid because there's 4 fluorines on there, but that's the HBF4. It yields the fluorobenzene. Okay, so what about H3PO2? What's that? What you mean? That's hypophosphorus acid. So hypophosphorus acid, when reacted with this diazo compound, it basically just forces that N2 to leave, and you get a hydrogen there, right? Why the heck would I want to I did all that work to make the diazo compound, but why would I want to make benzene again? Well, think outside the box, y'all. Remember that original tribromo compound that I wanted you to make? Well, what you can do is work your way backwards, right? Now I'm skipping some steps, right? But let's imagine, we know how if we had NH2 on there, we could easily polybrominate that benzene ring because nitrogen is a very strong donor, right? And we can work our way back to the aniline, right? And then back from there is our NO2 group, right? And then we know how to make that from benzene. So let's break it down. We hit the benzene with nitric acid, sulfuric acid gives us our nitrobenzene. We can reduce that nitrobenzene with H2, palladium on carbon, or we can hit it with tin or iron and acid, right? Either way, we're yielding our aniline, our amine, okay? Then we hit that amine with a little Br2 and iron 3 bromide, right? That gives us our polyhalogenated aniline, so 2,4,6 tribromoaniline. Little nomenclature for you. Then, of course, we take that amine, we hit it with some sodium nitrite HCl. That gives us our diazo compound. And then we hit that with hypophosphorus acid. That yields, that basically switches out where that nitrogen was for a proton or a hydrogen, and you get your tribromobenzene. So that's all she wrote. And so this is a cool reaction. The diazonium compound yields a lot of different products just from one step. And so you should definitely have that in your back pocket. I know it's not in this chapter, but definitely need to know it.